The ATLAS instrument on the ICESat-2 satellite measures elevation by timing the flight of laser light pulses that leave the satellite, bounce off the surface, and return to ATLAS. The speed of light is very fast, and so a regular stopwatch would give us too wide a range of time, a big margin of error. The timing has to be ultra precise, less than 1/billionth of a second, in order to measure the height of the surface within just a few centimeters.
I'm Phil Lors. I'm Deputy Instrument System Engineer on the ATLAS instrument on the ICESat-2 mission. Calculating the elevation of the ice is all about time of flight. It's time of flight of the photon from the laser down to the surface of the ice and back. So what we are doing is creating time tags of the transmit when the laser fires and time tags of the receipt of the photon. So it all starts with the transmitter. When the laser fires, it puts out billions and billions of photons. We pick off a little bit of that and we send it to a detector and we produce a start pulse. And that is the start of our timing system. The spacecraft sends us a position and attitude message every second that tells us where we are in the orbit. From that, we calculate where we think the spots are on the ground. We have a rough database of the whole Earth with elevation as it travels up and down mountains and down into valleys and over ice sheets. For each spot, we calculate where we think the surface is, and we open up a range window. For every photon that's received in that range window, we produce a time tag. Now, the sun produces a lot of green photons too, many more than our laser does. So our laser produces billions and billions of photons with every shot. If you add the noise in there, you won't be able to tell the sun's photons from the laser photons. So if you just took one shot, the one laser photon would be lost in the noise. But if you take 200 shots, now finally you have enough surface signal coming out of the noise that flight software on board can pick out this is noise and this is the signal from the surface. Once we downlink the photon time tags from the receiver and the transmitter, and we have the range windows, you put those all together, you have the transmit time tags, you have the time until the range window opened, you have the receive time tags in the range window. You calculate all that put together, it gives you the time of flight of a photon, which ultimately gives you the distance between the spacecraft and the ground. So if you know where the spacecraft is, and you know the time of flight, you know the distance to the ground, now you have the elevation of the ice.
Technology that can measure elevation adds a third dimension to how we map our Earth and allows us to study change across the poles and beyond.